Okay.
Awesome. So we can get started. Yes. So hello everyone. Good morning, good afternoon, good evening from different parts of the globe. Thank you so much, IOTCB, for giving us this opportunity to present our paper over here. We have prepared a presentation. We'll try to stick to 30 minutes of time that was allocated to us. And yeah, so I'm Bhavin Desai, product manager in Google Cloud, working on cross cloud network. And with me is Kapil Patil. Kapil, if you want to introduce yourself.
Yep. My name is Kapil. I work as a principal technical program manager with OCI, and I've been here for a year. I have worked at multiple companies in the same capacity as network capacity planning and network engineering as well.
Awesome. Cool. So let's get started. All right. So I think our topic is AI driven network capacity planning. Um, how you can use AI LSTMs to better plan your network capacity, and especially in a world where hybrid cloud is the new norm. It all started with data centers, then the public cloud came in, but nowadays what we see a trend is, according to IDC's 2023 report, almost 80% of the enterprises are going multi-cloud and hybrid cloud. So that's where we see a lot of customers heading towards, and the major issues that we see in planning the capacity. And in this presentation, we want to kind of go over, start with what the problems are, challenges with hybrid cloud, understanding the dependencies and the problems in planning for capacity, how LSTMs can be used for better planning, and we will kind of conclude with real world examples and the results that we are using in our day-to-day work in order to better plan for capacity. So with that being said, let's get started. So to set up the whole context of hybrid cloud or multi-cloud, what does it really mean? So if you, this diagram is a more of a logical representation of what a hybrid cloud looks like. This is where a company's IT infrastructure is kind of split between their on-prem data center, which in this diagram you can see what we are labeling as customer side, and on the other side is various cloud environments. These are public clouds like Amazon, Google, Oracle, Azure. So that's what it is, right? Hybrid cloud. So let's break down each component. So customer side, this is the place where the company has their own data center. This is how they've been operating for years, and it's literally a physical place or in a private facility where they host their servers, storage, have their on-prem legacy applications and critical workloads running over there. Now, customers still tend to use those because of several reasons like security concerns, compliance, and lot of integration and dependencies with the older existing systems. In the middle box, what you see over here, and again, this is just an example, it's an Equinix data center. There are a bunch of providers out there like Megaport, CoreSite, but just for illustration purpose, think of this as a co-location center provided by Equinix, and it has something called as a customer cage. This is a place which in the facility is kind of given or leased to the customer, wherein the customer can put in their equipments like networks, firewalls, servers, storage. And then there is something called as cloud exchange within that data center. This is basically Equinix platform that enables direct private connectivity from customers on-prem or customer site to multiple cloud providers. Um, there is a simple line of single link over there in the diagram that essentially represents the primary connection between the customer's on-prem data center and the Equinix facility. Now, customer also tend to host certain applications in this Equinix data center or within their customer cage. And most of the time, the primary reason is to achieve low latency for their applications. Now, there are several reasons for that. Number one is you want proximity to the cloud. So these applications are strategically kind of located close to the cloud exchange, in order to minimize network latency when interacting with cloud services. So a classic example would be to use a spanner database in Google Cloud, or RDS instance in Amazon Cloud, where you are actually hosting your MySQL database, and latency is super important to get consistency. Um, second reason is to get a better performance. Now, these applications need lower latency and better response time. A classic example of that is NASDAQ, a financial trading system, or on online gaming, where you need an instant response, and you can go as fast as speed of light. So that's why you go as close as possible to the cloud. On the right side, you see Oracle Cloud, and then there are other clouds like Amazon, Azure. This basically represents uh, a connection from Equinix Cloud Exchange to multiple cloud providers. This is the place where customers are hosting their applications. And nowadays, the new inflection point is the rise in the AI workloads. So all these cloud providers have their own forte in different AI services, whether it is Vertex AI in Google Cloud, or using Anthropic or Claude in Amazon, or using Oracle AI in Oracle Cloud. Also in Oracle, Oracle has this Oracle RAC or Exa database, which is uh, their primary or the most widely adopted databases across providers. So a customer who wants a multi-cloud and hybrid cloud environment through the Equinix Cloud Exchange can not only get access or private connectivity to Oracle Cloud, but also to other clouds as well as their on-prem. And that's how you are kind of establishing a private and secure fast connectivity between data centers and the cloud providers. So that's essentially from a high level what this whole hybrid cloud or multi-cloud environment looks like. Now, there are several advantages for this architecture, starting with the whole concept of hybrid flexibility. Basically, the company or the enterprise customer gets the best of the both worlds, right? Whether it is your on-prem data center, which is where you can host your sensitive application, but then you need agility and scalability and innovation. So then you can access the cloud to host certain workloads over there. You also are getting this private connectivity, which kind of helps you to secure your traffic, and also to get better performance, because now you're not relying on the public internet, which is succumb to certain internet weather events. And lastly, you as an enterprise customer get a choice. You as a company aren't locked into a single cloud provider, and you get the option to choose the best platform for each of your application and workload through this kind of architectural framework. Now, these are some of the advantages why customers do this, and this is a rising trend. But there are certain complexities and disadvantages to this approach. Number one is your overall complexity. Now you not only have to manage your on-prem data center, but you also have to think about your hybrid environment and multiple cloud providers, right? So you and your organization and the people working in the organization need to build expertise in both traditional IT infrastructure as well as cloud technologies. Then you need to think about different dependencies of cross cloud environments for your applications. How are you going to integrate and synchronize data between on-prem and cloud environment with lowest RTO and RPO as well? Also, there are certain, you need to think about certain points of failure in this architecture, right? How are you going to build reliability so that if one connection fails, you have another connection which can take over and has enough capacity to still maintain that workload or cross cloud dependencies. The next pillar is more around cost. While hybrid cloud does offer cost savings in the longer run, in the form of OPEX, reducing OPEX, it also requires upfront investment in the form of your hardware for on-premise data center, having presence in Equinix Colo, so on and so forth. You also need to start now paying for the bandwidth cost between the data transfer from your environment and cloud environment. And then you need to think about how you're going to manage multiple environments that can require additional staffing for specialized tools in order to maintain the operational complexity for this environment. This certainly tends to increase your initial OPEX, but in the longer run, your CAPEX is going down. And finally, latency. Even with low latency applications placed strategically, there might still be some latency when data and application interact across different environments. Also, if there is a failure in certain paths, your latency can bump up. So planning your diversity in fiber paths to reach the cloud environment while still maintaining consistent performance becomes an important consideration. Now, there are certain techniques to mitigate all of these above factors. Number one is you start with something called as careful planning. You need to thoroughly assess your requirements of your workload, create a budget for implementing this hybrid cloud strategy. Choose the right set of providers, like selecting the cloud providers that offers you flexible services, easy integration with your existing systems, and clear SLA guarantee for reliability. Focus on your security, implement robust security measures across all environments, ensuring that data in transit and data at rest are both encrypted, and you have the appropriate access controls and IAM guardrails. And finally, you need to monitor and optimize. Now, this is a continuous process, and continuously monitoring your cloud environment for performance, security, cost optimization, and figuring out the capacity planning is the key over here. Now, companies are increasingly adopting this hybrid cloud model to balance the benefits of both worlds, but there arises bunch of network traffic challenges with this. This flexibility of having hybrid cloud does come with a big cost of figuring out what is the right set of bandwidth I require between my on-prem data center and public cloud. And this reason is simple. Because the public cloud is highly scalable, that's why your network traffic patterns are highly unpredictable. It's think of it like a highway where you have number of cars that can suddenly surge or drop, making it difficult for you to allocate the right amount of network resources. So the repercussion of this is the cost of misprediction. As an enterprise company, let's say you underestimate the network needs, then you face slowdowns, right? You are going to have outages, your end customers are unhappy, you cannot go fast, and your agility reduces. But it's like a double-edged sword. Let's say you overestimated the network capacity. This leads to you paying a large amount of cost for unused bandwidth, and that's again a significant waste of money. So in this overall presentation, what we want to kind of touch base is AI as the solution. This is where your AI steps in. And later in the presentation, Kapil is going to talk about how we use LSTMs to analyze the historical data, the traffic usage patterns, and even external factors like a Black Friday event or a Cyber Monday event, and how AI algorithms can predict network traffic with a much higher degree of accuracy. And this allows enterprises to dynamically allocate resources, ensuring optimal performance and cost efficiency. Okay, so let's quickly go over understanding the whole problem of long-term dependencies. So for instance, let's say you want to understand a movie's ending. It really depends on the events that happened much earlier in the film, right? Similarly, network traffic patterns today are influenced by events from days or weeks ago. It's like a cyclic process of capacity planning, encompassing both proactive planning and reactive monitoring to ensure that an organization resources meets its current and future operational needs. Now, at the whole core of this diagram on the left side that you see is the whole concept of capacity management. Now, this is a central function that strives to maintain an optimal balance between existing available resource and what's the demand. This is achieved through this whole, let's call it a vicious circle of planning, implementation, and monitoring, and then again planning. So the key components over here are planning. This involves forecasting future demands, assessing the current capacity, identifying potential bottlenecks for improvement. This may include capacity planning, designing, and construction activities to ensure resources align with the project needs. The phase two over here is implementation. So once, let's say you have a plan in place, it needs to be implemented through your actions like IT implementation, building physical infrastructure, throwing fibers, buying more capacity from providers, and other activities. Next comes is the maintenance. Now once you have the capacity, the system is rolling, but you need to have a regular maintenance of this in check, as it is essential to ensure they can that these systems and this capacity can actually operate at peak efficiency. So this involves activities like monitoring, asset management, and predictive analysis to prevent failures and address issues proactively. Next in this cycle is the real-time monitoring. Now, continuous monitoring of resource utilization and performance enables quick identification of potential problems. These will allow your operational or SRE team for timely intervention to prevent disruptions and ensure smooth operations. And then finally is the whole concept of predictive analysis. By analyzing the historical data and patterns, predictive analysis can help forecast future demand and then identify potential capacity constraints or bottleneck before they become critical in your paths. So the cyclic nature of this diagram essentially emphasizes the capacity management is kind of an ongoing process in large enterprises, and continuous monitoring and analysis allows for proactive adjustments to capacity plans and resource allocations, ensuring that your organization remains agile as well as responsive to the changing and dynamic needs. Now, why does traditional methods fail? So the traditional network planning often relies on this whole simple trend lines or outdated assumptions. It's like a graph with straight line prediction that clearly misses the mark compared to the real fluctuating data. And that's where this whole concept of LSTM, the memory experts, came into usage. The long short term memory networks is a type of AI designed to excel at handling long term dependencies. Um, LSTMs have special memory mechanism that helps them to remember important information from the past and then adapt to changes in the future. There are three major functionalities within the LSTMs if I have to break it down for you. One is predict. So LSTMs can anticipate spikes in traffic before they even happen, giving you time to scale up your resources. Second pillar is the adapt. It continuously is learning and refining its predictions, so it's always one step ahead of the curve. And then finally is optimize. So LSTMs can help you allocate resources more efficiently without over provisioning, and so it will help you to save cost as enterprise as you start growing your network. Now I'll hand it off to Kapil to go over into more details of how LSTMs work and how it's been implemented in a real world scenario, and finally concluded with the results. Kapil, please go ahead.
Yep. Thank you, Bhavin. So on this slide, we'll basically talk about briefly on how LSTMs work. But before that, there are like three diagrams here. One is neural networks, the other is recurring or recurrent neural networks, and the third one is LSTMs. If you consider a family tree, neural networks are considered the top of the chain, RNNs come under that, and LSTMs are one level below that. Now, in this case, if you look at the neural networks diagram, you can see that neural networks are made up of interconnected nodes or neurons, as we call them. These neurons receive input, they perform certain operations, and then they send outputs to other neurons, and you can see the red one as the output layer. And the next one is basically RNNs. RNNs are, you can consider them as a specialized neural network design to process sequential data, such as text, speech, or even time series events. the connections have a loop back to themselves. You can see the first portion where it's looping back to itself. This allows information to persist from one step to other. The next one is LSTMs. Now, LSTMs are generally and even more, I want to say, specialized versions of RNNs. LSTMs were created to address a very specific shortcoming that the basic RNNs was very visible with the basic RNNs. The difficulty of remembering information over a long sequence. Uh, LSTMs use a concept called as gates. That is how they control the flow of information within the network. If you look at the LSTM diagram on your right, the entire thing is called as the memory cell. Inside those memory cells, there are information flows and there are selective memories. Information flow, you can consider them as conveyor belts, where information flows from one step to the next, or each cell state to the next. This allows LSTMs to remember information unlike RNNs. That's the biggest advantage. And then the second part of that is the selective memory. Unlike regular neural networks that tend to forget older information, LSTMs can selectively keep some information and discard whatever is not needed. And that is what is crucial for the task when it comes to network capacity planning. Because there are so many intricacies involved, as Bhavin explained in the previous slide, we want to make sure that there are certain memories that the LSTM module remembers, based on which it can predict the next layer of traffic when it goes forward. LSTM also has a concept called as gates. The gates are basically the decision makers. Forget gate, input gate, and output gate as three of the main elements of the decision making. They decide on what information to remove from a cell, which information to add to a cell, and what information to output from a cell. That's how LSTMs, in short, generally work. As I said, when it comes to sequential data like text, speech, audio, RNNs and LSTMs both process sequential data when the order of the input matters. But when it comes to remembering certain sections of the data, RNNs can do the basic function of it, but LSTMs come into play when because they have a very sophisticated memory mechanism that allows them to learn and remember longer term dependencies in a data. Bhavin, next slide, please. Thank you. So in this slide, what we are going to look at is how do we use the current data collection that we have, current data collection models that we have, and feed it into our AI model as a continuous method, which helps us generate the predictive capacity. And we'll see that in the next slide. So AI-driven capacity. So in this particular slide, you can see that on the left of the data collection slide, we have specific elements such as the network traffic, we have the workload, we have threat IPs, we have security group changes. We take a lot of this input data, and this also includes the current topology of the network, and feed it into our AI model. Because as I said in the previous slide, network capacity planning has very, very intricate levels of elements involved in it. So we want to make sure that the data or the output that we get is as close to reality as possible, which is why we are also inputting certain ensemble learning techniques like random forest, or we are also using gradient boosting in that. This will only help us get an even more cleaner data, predictive data, and closer to reality as much as possible when it comes to predicting traffic over 6 months, over 3 months, or even over 2 weeks. Bhavin, next slide, please. Okay, so let me go through this concept very quickly, because this is important for the model that we have developed. It's called as a dynamic resource allocation, or DRA. This basically consists of 5 different elements. One is the AI model. That is where your initial process starts, where you submit your very, very clean network data. And it's the first initial version of our cyclic process. The second one is predictions. This is where the model that we have used creates your first set of predictions based on the clean historical data that we have given. Now, remember that this prediction is not the true prediction. This is just based on the first element of memory that it has put into it. It's a very cyclic and iterative process. It will keep on relearning based on the data that we feed, and that the predictions become even better and better as we go forward. The third one is resource adjustment. Based on the predictions that the model will make, we can adjust our resources like memory, power, how many servers do we want to put into our network, how many routers or switches do we want to put into our network based on the incoming traffic that will be over the next set of period. All that is done in the resource adjustment module of this methodology. The fourth one is network monitoring. This is where the model will, the deployed model will keep on continuously monitoring for any issues based on how many resources it has deployed. And then the fifth one is learning and improvement. This is where it's a loop back iterative process. The data collected during monitoring is used to evaluate the model's accuracy. The feedback from the monitoring and the prediction helps us identify areas where the model can be improved. And you can see it's basically a loop back process. It basically loops it back over again to the making predictions. And that's how the prediction making module improves over time. There are key advantages when it comes to DRA, and that's why we specifically chosen this model. Optimal resource utilization, that's where it enables us to not over provisioning or under provisioning certain resources in our network. Enhanced scalability. DRA allows to quickly adapt to changing demands. If there's a sudden surge in traffic, let's say the AI model can automatically scale up resources or scale down resources to handle that incremental or decremental amount of load that is going onto the network. The third one is improved performance and reliability. By utilizing resources accurately, our DRA model minimizes the risks of service disruptions and ensures a smooth operation. The fourth one is reduced manual intervention. That is the main objective of introducing AI into capacity planning process, because as Bhavin said, some of the examples as Black Friday or Cyber Monday, these are very big events in the United States where you can't really predict how many people are going to literally use our cloud for one reason or the other. So in order to remove the manual intervention, the AI-driven nature of DRA helps us out on a large scale. And then finally, the last one is cost effectiveness. Because we are optimizing our resource allocation using DRA for either over provisioning or in order to prevent over provisioning or under provisioning, it's in a way also helping us maintain our costs in a certain to a certain extent. We are often in cloud, as you may have heard, we are often billed for our usage. So with this, what we are trying to do is we are trying to make sure that we only provision certain amount of resources in our network that will help us drive our cost effectiveness to the maximum variance that is possible. Next slide, please. Okay. So the next slide is basically methodology. This is a recurrence of the previous slide, but I'm going to go over this quickly. There are three main layers to our methodology. One is data pre-processing, the second one is data training, and the third one is data evaluation. Data pre-processing is where we feed in very clean historical network data. The model handles any kind of missing values, and it performs feature engineering to extract relevant features and relevant details from that data. The second one is model training. This is where we split the pre-processed data into training and testing sets. We use ARIMA models for our training sets. That's how we have developed the model in the backend. And we determine optimal values for autoregressive, differencing, and moving averaging parameters in this specific layer. And the third one is model evaluation. That is where we evaluate the model's performance on testing very specific set of metrics like MAE and RMSE. We compare forecasting accuracy against traditional methods and other ML techniques at this specific layer as well. Bhavin, next slide, please. Now, before I go into showing you the actual results of our model, I just wanted to go over this specific slide very quickly. This is a very traditional, I want to say, how a cloud network looks like in the backend. Many of you may not be visible to how internally a cloud works, but in the backend, any cloud host like AWS, Amazon, Oracle, and this network diagram is not specific to any one of them. This is a generalized form. What we as cloud providers have is we have three layers of entry. One is our backbone routers, one is our fast connect or direct connect. These are the peer-to-peer connections that we offer our customers. And then the third one is internet. These are the three ingress points for us. These come and hit our networking layer. And then through the networking layer, we have different layers or networking layers for each of our fabrics for each of these layers. There's a backbone fabric, there's an internet fabric, there's a fast connect fabric, which handle this incoming capacity for us. And the last one is metro fabric. Metro fabric is where we have, oh, I think Bhavin dropped off. Give me 1 second. Let me see if I can present it.
I'm sorry, it got disconnected. I had a blip.
Oh, okay. Okay, no problem.
Sorry about that, folks. Yeah.
Yeah, no worries, man. Thank you. Okay, so metro is where we basically have redundancy in our networking model. We just don't take in customer data onto our one data center and pass it down to your compute layer. We actually have multiple data centers in the backend, and that's how we connect to each other through the metro layer. And from the metro layer, each of your compute block, storage block, data network block, whatever blocks that you are utilizing are into our children's sites or child sites, as we call it. We again connect to children's sites through our metro network, and within our child sites, we have a different networking layer, which is isolate or which is different from the parent networking layer that are in our POPs. It has again its own networking layer. It has its compute layer. So if you can see, if the packet enters through our backbone routers or through our internet routers or through our peer-to-peer connection services like Fast Connect or Direct Connect, it has to go through all of these networking layers until it reaches your compute blocks. The compute blocks is where you actually spin up your virtual servers and you run your environments. So we have to manage the capacity of so many different layers to make sure that you are getting very least low amount of latency that you have agreed to as part of your SLA and the highest network connection or network connection speed that you request from us based on which layer that you're coming from. So I just wanted to give this behind the scenes scenario when it comes to capacity planning and how many layers do we have to really look at. In the next slide, we will basically look at some of the results of our monitoring. So what we are doing right now is we are currently in the first box that you see, we are currently asking the model to play 4 different scenarios for us. Those 4 different scenarios are, we are trying to fail all the routers in the network one by one based on the last 7 days of LSP data in steady state. We are also doing the same with SRLG. And then the 2 different ones that we are doing in order to proactively see how much capacity can we plan for in the next 6 months is we are incrementing 30% of traffic on top of what we see right now. So all of these 4 layers help us understand from our network perspective, how is the traffic going to behave if we expect a sudden surge of traffic and if we need to allocate resources accordingly. The second block on the lower left-hand side that you see is one of the results of the model. What that tells us is the first column is the routers that we are failing one by one, and we have given them names according to airport codes because that's like a standard among all cloud providers. The second column that you see is the affected region and affected source region and affected destination region. So I'll tell you what that means on the third block on the lower right side. What that means is, let's say if we are failing one of the routers in YYZ, which I believe is Montreal, it's going to affect the traffic between Montreal to Toronto. And the way that it is going to affect is, you can see the steady state path is a direct path between Montreal and Toronto that we have already in the network. It's giving us a direct latency of 4.5 milliseconds to send the traffic from Montreal to Toronto. If we fail that router, the traffic will take an additional hop through LaGuardia because that's where we have another data center of ours, because the primary path has gone down and the latency will increase to 9 milliseconds. Now, based on this data, what we can do is we can allocate more capacity on diverse path between Toronto and Montreal so that the traffic doesn't take the hop onto the backup route and our customers can get the least amount of latency that we have promised them to. A similar one you can see on top of that is between routers between Jeddah and Abu Dhabi. So let's say there is a direct path between, there is an indirect path between Jeddah and Abu Dhabi, which goes via Dubai. If that complete path fails down, the backup path will go through Marseille, MRS, and it will come back to Abu Dhabi because that's how the network, that's how we have physically laid the network capacity in our background. So that's again helping us determine that the latency is increasing from 70 milliseconds to 65 milliseconds, and we need to augment our path between Jeddah and Abu Dhabi through Dubai so that we don't have our customers' traffic move through Marseille in the backend, and then they experience that additional latency. So that's how our model is helping us make decisions on exactly how much to increment on which path and how to ensure that we have diversity for our customers and we are exactly giving them what they signed up for as part of their SLAs. Next slide, please, Bhavin. I'll just quickly go over what the real world validation and the future for our model looks like. So as you saw, because the model can accurately pinpoint us on where exactly to augment and how much augment by, we have seen an 18% reduction in our cost. That's close to $10 million annually. It might sound a big amount, sound like a big amount, but believe me, when it comes to networking, and especially when it comes to bigger organizations like Google or Oracle or Amazon, that's a very, very small amount. But it's still, if we calculate that amount over a certain period of time, over 2 or 3 years, it tends up to become an incremental and exponential savings for us that we can use for some other projects that we have. The second one is uninterrupted performance. Because we are monitoring very specific performances because of our AI model, the seasonal fluctuations, sudden spikes in the network, they don't affect us as much as they used to do before. We have uninterrupted performance internally so that it can help us give uninterrupted performance to our customers. The third one is tackling complexity. There are complex type of, let's say an example, if there's a Black Friday event going on where there's a lot of traffic being pushed to our network, but at the same time, one of our big customers starts to test one of their applications onto our cloud, which again sends us a big surge of traffic. Now, this is a complex traffic scenario where we have to manage 2 different big events. This model is actually helping us to accurately predict how much traffic is going to increment if certain unforeseen circumstances come into our play, and we can augment our traffic accordingly back and forth. And the last 2 are building through transparency and continuous adaptation. Building through transparency, you can see AI model is kind of a black box. So we are working on something called as explainable AI or XAI, where we are diving into the exact workings of why AI takes certain decisions that it takes. And continuous adaptation is because it's a real-time loop. We are continuously feeding it data through our monitoring metrics and through our events that are happening, and we are trying to make the prediction model as better as possible so that it can help us with even more cost savings and uninterrupted performances for not only us, but for our customers as well as we go forward. Bhavin, next slide, please. And then finally, I want to end the slide deck with our conclusions. Hybrid clouds, as Bhavin spoke about, are flexible and they provide scalability not to us, but also to our customers. We saw that how network traffic is such a big challenge, especially as we go ahead with AI, LLM, Gen AI, or when all of these models are coming up, it's putting a lot more pressure on clouds. And that's why the challenge is becoming unpredictable, and finding a way through this unpredictable challenge is something that we are trying to do. We used LSTMs and time series forecasting in our model in the background, and we showed how it offers a smart solution when it comes to network capacity planning and takes away from a lot of manual efforts that we had to put compared to a traditional capacity planning process. And finally, we showed some real world test results, which showed us instant cost savings as well as performance boost with uninterrupted performance that we received for us. And then indirectly, we showed it for our customers as well. But that was the last slide for us. But thank you for giving us an opportunity to present here.